Hello, chemistry students. Today we're going to talk about the ideal gas law. The ideal gas law is PV is equal to nRT. Now, we've been talking about other gas laws, Boyle's law, Charles' law, Avogadro's law, and Gay-Lussac's law. And with those, you've always had more than one pressure, or more than one volume, or more than one temperature, or more than one number of moles. With an ideal gas law, you know you have that kind of a problem when you are only given one set of values instead of two sets. So you're only given one pressure, or one volume, or one temperature, or one amount of something. Now the P stands for pressure, V stands for volume, N stands for the number of moles or the amount of a gas. R is the ideal gas constant, and we'll go over that in just a minute. T is the temperature. Now remember, temperature always has to be in Kelvin in our ideal gas laws. The volume must be in liters. Now if we look on our star reference sheet, we'll notice that the ideal gas constant, R, has three values. It is 0.0821 liter atmosphere per mole Kelvin, or 62.4 liter millimeters of mercury per mole Kelvin, or 8.314 liters kilopascals per mole Kelvin. Now the R that you will use in your ideal gas constant, if it's 0.0821, 62.4, or 8.314, depends on the pressure that you're given. If your pressure is in atmospheres, you're going to use the 0.0821. If your pressure is in millimeters of mercury, you're going to use the 62.4. If your pressure is in kilopascals, you're going to use 8.314. Now let's do an example calculation. How many moles of oxygen must be put in a 0.500 liter flask at 20 degrees C to have a pressure in the flask of 1.77 atmospheres? Let's write down our variables. So it says how many moles, so that means we're looking for N. So N equals, and I'm going to put a question mark here, 0.500 liters is a volume. And it is already in liters, so that's good. We don't have to do any conversions. Our temperature is 20 degrees C. Temperature must be in Kelvin, so I'm going to go ahead and convert that now. And that is 293 Kelvin. To convert temperature or Celsius to Kelvin, all I do is add 273. And the last thing is pressure. Our pressure is 1.77 atmospheres. Now, I know this is the ideal gas law because I'm only given one set of each of these variables, which means I need to find out what R is. So I'm going to go ahead and put R equals. Now let's look at our star reference sheet. And our star reference sheet gives us the R values. And my pressure is in atmospheres, so I'm going to be sure to use the R that is in atmospheres, which is 0.0821. And my units are liter atmosphere per mole Kelvin. Now that we have all of our variables, I need to rearrange this formula to look like N equals, since that's what I'm looking for. So how I do that is I look for the variable that I want to keep on this side, and that is N, and I see how it relates to all the other variables that I need to move to the other side. Now this is N times R times T, and since it is multiplied, I have to do the opposite, which is division. So I'm going to divide both sides by the variables that I want to move to the other side, which is R times T. So I'm going to divide both sides by R times T. And when I do that, I have an R on top and an R on bottom, they go away. I have a temperature on top and a temperature on bottom, they go away. And I'm left with N is equal to pressure times volume divided by the ideal gas constant times temperature. Now all I have to do is plug in my values. N is equal to pressure, which is 1.77 atmospheres, times volume, which is 0.500 liters, divided by the ideal gas constant, which is 0.0821 liters, atmospheres per mole Kelvin. Now, since it's per, this is our per line right here, our divided by, okay? Now, remember, the number has to go next to the units that are on top. So the units on bottom are going to go on the opposite side of the line, which is why I put them up here. Now, times temperature, and my temperature is 293 Kelvin. Now I am going to cancel my units that I can. I have an atmosphere on top and an atmosphere on bottom, so they go away. They cancel. I have a liter on top and a liter on bottom, so they go away and they cancel. I have a Kelvin on top and a Kelvin on bottom, so they go away, they cancel, and I'm left with moles, which is what I want to be left with because I'm looking for moles. So N is equal to 1.77 times 0.5 divided by 0.0821 times 293. And that is 0.0368 moles. Now let's do another problem. We have 1.17 grams of helium are put into a 500 milliliter container at 10 degrees C. What would be the pressure of the container in millimeters of mercury? So we have moles, but if you notice here, this is grams, and we need to convert this into moles. So let's go ahead and do this. Now, whatever units we have on the top, we always put on the bottom, and we're looking for moles. If it's a mole gram, not a mole mole, we always put a 1 next to the mole. And grams per mole, that's molar mass. So we're going to look on our STAR reference sheet, the periodic table, for the molar mass of helium. Helium is 4.00 grams per mole. So 1.17 divided by 4 is equal to 0.293 moles. Our volume is 500 milliliters. It has to be in liters. We need to go ahead and convert this. I know that there are 1,000 milliliters in 1 liter. So 500 divided by 1,000 is 0.500 liters. The next thing is temperature. I'm going to draw a line right here. Temperature we have is 10 degrees C. We know we have to convert that to Kelvin, so I'm going to add 273. 273 plus 10 is equal to 283 Kelvin. Pressure, that's what we're looking for. This is an ideal gas law because we're only given one of each of the variables, so I know I need to find R. And it says that our pressure needs to be in millimeters of mercury. So I am going to look on our STAR reference sheet for the R that we're going to use. And it says here that the R that uses millimeters of mercury is 62.4 liters times millimeters of mercury divided by mole Kelvin. Since we are looking for pressure, I need to rearrange this formula to look like P equals. And so in order to do that, I look at how the variable that I want to keep, which is pressure, is related to the variable that I want to move to the other side. It's P times V, so I have to do the opposite of that. The opposite of multiplication is division, so I'm going to divide both sides by V. When I do that, my V's cancel over on the left side. I have a V divided by a V. So they go away. And my formula that I'm left with is P is equal to N times R times T divided by V. Now I'm going to plug those in. The number of moles I have is 0.293 moles times my R is 62.4 liters times millimeters of mercury per mole Kelvin. My temperature is 283 Kelvin, and I'm dividing by my volume, which is 0.500 liters. Now I'm going to cancel out my units. I have a mole on top and a mole on bottom, so they go away. I have a liter on top and a liter on bottom, so they go away. I have a millimeter of mercury on top, but I don't have a millimeter of mercury on bottom, so I'm going to keep that. I have a Kelvin on top and a Kelvin on bottom, so they go away. Now I'm going to multiply 0.293 times 62.4 times 283 divided by 0.5, and I get 10,300 millimeters of mercury. Thanks for watching.